Mama told me. Yeah. Come on. Mama told me. One day I'ma grow up big and
Hey guys, what's going on? It's Pete. Today we get to talk about the clash between ideal and real gases. And so it's only Pete here. We had a previous video on the ideal gas law. Me, Wallace and I, we talked about the ideal gas law, and as a side note, we talked about how like ideal gases can appropriate exactly the behavior of real gases, but they come close to it in certain conditions. But Wallace was in Venezuela, and I had to go to Venezuela because he had gotten mauled by a cat. He has suffered some fatal injury. We might be staying in Venezuela for a long time. I don't know, guys. So yeah, again, the question was why do we have an ideal gas law that doesn't appropriate real gases correctly? Well, exactly, right? So one of the beliefs of the ideal gas law was that molecules do not take up space, and we know this isn't true. All molecules have some sort of volume they take up. And molecules do not attract each other was another part of the ideal gas law and a condition that needed to be satisfied. We know this is not true either. There are several intermolecular forces, and ideal gas laws believe that there were elastic collisions between molecules of gas. We know this isn't true either. So each molecule has a certain degree of what we call stickiness, right? So they do have inelastic collisions. They're not perfectly elastic. So yeah, these were wrong. So when does the ideal gas law work best? We have a low pressure and a high temperature. So at low pressures, it makes sense because with Boyle's law, if we have a low pressure, that means that we have a high volume, and the individual volume of the molecules added to the volume to the total volume of the system will be very negligible. But at high pressures, we have very low volumes, and if we have low volumes, when we add the volume of the individual molecules, it might drastically change the overall volume of the system. Now at high temperatures, well, one of the beliefs of the ideal gas law was that we have no intermolecular forces, and at high temperatures, the intermolecular forces become very negligible. Collisions become closer to elastic because molecules are moving at such high speeds. So we have something called a compressibility factor. Real gases are not really appropriated by ideal gas law. So we have a Z, right, our compressibility factor. It's PV over nRT. So as from our ideal gas law, this should equal 1. So that's the line y equals 1. But here we have what actually happens. So on the x-axis, we have our pressure, and on the y-axis, we have our factor. So the x-axis is as pressure increases, right? And the different curves are at different temperatures. Now we notice that as we increase the temperature, the curve gets closer to y equals 1. But as we decrease it, well, it gets way far off. Another way just to look at the ideal gas law and see how it doesn't really work for real gases at certain conditions. But real gases deviate from ideal gases at certain conditions. So what do? So there's several models that appropriate the behavior of real gases, and modern examples are very complicated, but the one we're going to be looking at here is the van der Waals model. So it basically states that P plus AN squared over V squared, that quantity times V minus Bn equals nRT. So all the values we had from our ideal gas law, so P is our pressure, V is our volume, N is the amount of gas or the number of moles, R is their gas constant, and T is the temperature. But now we've introduced two new variables to the equation A and B. And A basically describes the intensity of intermolecular forces in the gas, and B is the emitted volume per mole of gases. So we are correcting the pressure and the volume of the system. All right, so we have a problem. 1 mole of carbon dioxide at 400 Kelvin occupies 700 milliliters. What is the pressure of the gas according to van der Waals? So A is 3.61 atmospheres liters squared over mole squared, and B equals 0.0428 liters per mole. All right, so we look back at the equation and we want to plug in our values. So first thing we need to do is list out what we know and what we don't know. We're looking for the pressure, and this is everything else we do know, okay? So list those out. Okay, now we have our actual solution. So we have X atmospheres, the pressure, plus 3.61, that's our A constant, times the volume squared, times the number of moles squared, which is the 1 squared, right? We only have 1 mole, over the volume squared, which is 0.7 squared, which is 0.49. So that whole quantity times, so the volume, 0.7, minus Bn, so B is our 0.0428, and N, that number of moles is just 1 again. So we subtract the 2, and we get, this is equal to nRT, so number of moles again, it's 1, times the gas constant. Look at our other video on ideal gas law if you don't know what the gas constant is, which is 0.0821, since we're working with atmospheres, liters, Kelvin, right, whatnot, and 4 times 400 Kelvin, right? So we do the math, we put X onto one side, and we get that X is 42.6 atmosphere. But the more you know, the better you are. So-called life they call living, but I call it strange, and I bet I'll do it, 'cause I'm on my way.